example 1, $500 is put into a savings account, so that is my principal, and an 8% annual rate, so I know R for annual is 8%, compounded continuously, and calculate the annual yield. So we are using the model above. Okay, so activity shows that when n is large, this is the paragraph before example 1, activity shows that when n is large, it can approximate e to the r. We just talked about that. Since e to the r minus 1 is the annual yield, the limit indicates that as the number of compounding periods increases, the annual yield is e to the r minus 1. When this yield is used to calculate interest, the interest is said to be compounded continuously. So we're calculating the annual yield. Annual yield is going to be, so part A, that formula is e to the r minus 1. So our rate is 0.08. So e to the 0.08 minus 1 gets you e to the 0.08 minus 1 gets you 0.08328, rounds to 9. Okay, and our book writes this as approximately 8.329%. They're using more decimals to be more exact because we're using, our calculator uses E, but our calculator also could be using the approximation for it. And then after 1 year, the account grows to. So this is the percentage you're going to end up with after a year. Every year you're going to be getting 8-ish% of your money back as interest, even though it's compounded continuously. So it's not like, oh, after 3 months I'm getting this exact rate because every month I get 8%. It's not every month you're getting 8%. Yearly you get, well, every time it's being compounded you get 8%, but that's continuously. So overall, every year you get 8.329%. So after 1 year, you started with $500, and then after 1 year, you're going to get $500 with the 8.329% and figure out your total from there. To be more exact, they're doing 500 plus 500 e to the 0.08 minus 1. Plugging this whole expression in is more exact than the above. We've also seen this. You could also just say this is 500 times e to the 0.08. Because this minus 1, well, we're adding 500. Instead of subtracting 500, we're already adding it. So you could just plug this whole expression into your calculator. And you should end up with approximately $541.64. So after 1 whole year, you're going to end up with that in your account. So $41.64 of interest. The continuous change model is allowing us to not have to write this for E. We can actually just use E in it, and we don't have to have, we're changing our model from this. Remember, this approximates E to the R, so the continuous change model puts in E to the R, but still to the T power. So example 2 says, suppose we use the same stuff. So I have A equals 500 as our principal. Our interest rate is 0.08 for however many years we plug it in. After 4.5 years, so if T is 4.5, in part A, 500 times E to the 0.08 times 4.5, I'm going to end up with 716.66. I rounded 2 decimal places because this is money, and that's a 1. So $716.66 after 4.5 years. How does this balance compare with quarterly compounding? So if we flip the page, we can see what formula they used. So on page 584, flipping the page, for part B, the formula they're using for quarterly is one that we've seen before. That's not N, I want R. R over N to the NT, okay? But quarterly means there's 4 times a year you're getting it. So I have my principal of 500, my annual rate is 0.08, dividing it by 4 times a year, which you've seen that part before where they divide it by the number of times per year. I get it 4 times per year, and I get it for 4.5 years. Now what does my calculator tell me I get? So 500, okay, I'm going to do this differently. 0.08 divided by 4, add 1 to the 4 times 4.5 exponent times 500. That way I don't need parentheses. 714.12. Okay, so compounding continuously is better by how much? About $2. A little more, but basically $2. So compounding continuously is better for your buck and your investment. All right, natural logarithm definition. So natural logarithm is log base e of x is y. So y is the natural log of x. You can also write this as just natural log of x. If you write ln, it's assumed that it's a log base e. So just like clicking the log button tells me it's just a log base 10, if I click the ln button, this is a log base e. They are assumed because they are used so commonly in everything. Example 3. So, it is wordy. Under certain conditions, the height in feet above sea level can be approximated from the atmospheric pressure P in pounds per square inch, using the equation there. Human blood boils at 0.9 psi, and such a situation is fatal. Who knew? At what height above sea level will blood boil in an unpressurized airplane cabin? So, they're telling us our formula is h equals natural log of p minus natural log of 14.7, all divided by negative 0.123439. That's 4 decimals, right? Yeah. 4. All right, so the only unknown in here is h and p, but they're giving us a p of 0.9 because that's when human blood will boil. So if I plug that in, I'm going to be getting natural log of 0.9, clear, natural log of 0.9, enter, minus natural log of 14.7, enter. So that's my numerator. Now I'm going to divide by the denominator of negative 0.123439. So 71620.71819. And they're not telling us where to round. So approximately 71,621 feet above sea level will be when our blood boils. And the last reflection question for you is, how are natural logarithms related to exponents? And give at least 2 ways. If you want to communicate or share this with me, come to office hours, or you can post them in the attendance question for this week.